Hello, welcome to a new lesson where we study the Hamilton-Jacobi formalism, and we are looking to the topic of the Liouville's theorem, right? And we are going to look to two examples of how to use this theorem to find a solution to the Hamilton-Jacobi equation associated to a particular mechanical system, which is in this case the particle that is under the influence of a gravitational field that is uniform, right? So in that case, we only have a particle that has a mass m. Yeah, it is falling, right? Well, in this case, this is a motion that can be in two dimensions, right? It can be falling in this direction, maybe, or just in the y direction. But the thing is that the gravitational field is uniform and it is under an acceleration of g, right? So we know that the Hamiltonian for this particular case is equal to px squared plus py squared divided by 2m, and then plus mgy, right? Perfect. This is like the function that describes the mechanical system. Here, of course, these px and py, they represent the linear momentum in the x and y direction respectively. And like I said, m is the mass and g is the acceleration of gravity, right? So what we are going to establish is a new quantity that is px py divided by m plus mgx that turns out to be very special because it is a constant of motion, okay? And we are going to show that it is a constant of motion because it is going to be important. First of all, you should know that, well, for example, let's say that we have a function f that is of the coordinates qi and pi. What happens if we want to calculate the derivative with respect to time of this? Well, that is going to be f dot, and we can see that using the chain rule, this is going to be the partial of f with respect to qi, and then the derivative of qi with respect to time, plus the derivative of f with respect to pi, and the derivative of pi with respect to time. Perfect. But we know that there is something known as Hamilton equations, that it tells us that this quantity that we have here is equal to the partial of h with respect to pi, and this quantity is equal to negative the partial of h with respect to qi, where h is, of course, the Hamiltonian of the mechanical system. So we know that f dot is equal to the partial of f with respect to qi, the partial of h with respect to pi, minus the partial of f with respect to pi, and then the partial of h with respect to qi. But we know that from a basic course in classical mechanics that this quantity can be defined as the Poisson brackets of f and h, right? This is the formal definition of the Poisson brackets. Okay, perfect. So this means that the Poisson brackets with the Hamiltonian, right, allows us to calculate the derivative with respect to time of a function f, right? So that means that if the Poisson brackets of the function with h is equal to 0, well, that means that that function is a constant of motion, right? Because the derivative with respect to time of the function is equal to 0. So what we are going to do is to calculate the Poisson brackets of this quantity with the Hamiltonian h, and then we are going to see that that is equal to 0, right? So let's establish that the Poisson brackets, let's say h with px py divided by m plus mgx, and this is px squared plus py squared divided by 2m plus mgy, comma, px py divided by m plus mgx, right? And how are we going to calculate this? Well, we can use a lot of properties, right, that you know that the Poisson brackets have. So we are going to calculate some part of this with the properties and other part with the definition, just to practice, right? So let's use distributivity first to say that this is going to be the Poisson brackets of px squared plus py squared divided by 2m with px py divided by m plus the Poisson brackets of px squared plus py squared divided by 2m with mgx, and then plus the Poisson brackets of mgy with px py divided by m, and then plus the Poisson brackets of mgy with mgx. Okay, and here is an important fact. You should know that if you have the Poisson brackets of the generalized coordinate, let's say qi, with the conjugate momenta, let's say pj, right? This is the Kronecker delta ij, right? Okay, so for example, if we have the Poisson brackets of x with px, this will be equal to 1, right? Okay, perfect. So, and for example, if we calculate the Poisson brackets of y with px, this will be equal to 0 because we are working with a different index, right? And for example, the qi's with the qj's are going to be equal to 0, and the pi with the pj is going to be equal to 0. This is important because it is telling us that only when we calculate the Poisson brackets of the generalized coordinate and its conjugate momenta, we are going to get something different from 0, right? Well, this is a consequence of the definition, right? If you use the definition, you can show very easily these relations that I have here. So the thing here is that if we notice these Poisson brackets, we are going to see that we're calculating, for example, in this piece, the Poisson brackets of only conjugate momentas with other conjugate momentas. So that means that this is all going to be equal to 0. I mean that we can establish some properties, right, to deconstruct these Poisson brackets to get something of the form px with px, or maybe py with px, right? But the thing is that all these pieces are going to be equal to 0. So that means that all the Poisson brackets that we have here is going to be equal to 0. Perfect. Notice here that we have the conjugate momenta of x, and we have an x here, right? So when we calculate the Poisson brackets of this piece with this piece, it's going to be different from 0. So that element is going to survive. And that will happen again with these Poisson brackets, right? We have the y here, the py here. So this is going to survive. But in this case, it's going to be different, right? Because we have the y with the x. We know that that is going to be equal to 0. Okay, perfect. So what is this going to be? Well, let's establish that here we can separate this element with this element. I mean, to take the Poisson brackets first of this element with this, and then take the Poisson brackets of this element with this, right? But that last one, this one, is going to be equal to 0, right? Because we have py with x. So that means that all this is going to be the Poisson brackets of just this quantity with this quantity. Okay, perfect. So we are going to establish that this is going to be equal to the Poisson brackets of px squared divided by 2m with mgx. Okay, and let's continue with this. What is going to happen here? Well, okay, we have a product here, right? So we know that there is a property of the Poisson brackets that tells us that we can take out each element, calculate the Poisson brackets that is left, and then sum the Poisson brackets, but now taking out the other element, right? But remember that if we take out, for example, the py, we are going to get the Poisson brackets of y with px, but that is 0, right? So we need to take out the px, and to get the Poisson brackets of y with py, that is going to be equal to 1 times a constant, right? That we are about to see what constant that is. But the thing here is that we are going to get the px that multiplies on the number 1 and a constant. So we are going to take out that px to get plus px here. And that constant that I mentioned is, well, mg divided by m, right? But we can cancel the m to get g here. and then the Poisson brackets of y with py, right? Okay, perfect. So we mentioned that this is equal to 1. And what are we going to get here? Well, here is where we are going to use the definition. Okay, we can solve it by using the properties, but again, just to practice, we are going to use the definition. So here we are going to get pxg, and then plus, what is this going to be? Well, remember that first we need to take the derivative with respect to the coordinates, the generalized coordinates, right, of the first function. So this is going to be the derivative with respect to x of px squared divided by 2m, the derivative with respect to px of mgx, which is clearly going to be equal to 0. And then we need to do the same thing, but with the y, right? So this is the partial with respect to y of px squared divided by 2m, the partial with respect to py of mgx, which is again going to be equal to 0. Okay, and then, well, the Poisson brackets definition tells us that we need to subtract the derivative with respect to px of px squared divided by 2m, the derivative with respect to x of mgx, and then subtract the derivative with respect to py of px squared divided by 2m, the derivative with respect to y of mgx. As you can easily see, all this is going to be 0, this is 0, and this is 0, right? Because here we are taking the derivative with respect to py, so it is 0. Okay, so we get that this is pxg minus, and here notice that we will get from here an mg, and from here we are going to get 2px divided by 2m, which is px divided by m. So that is px divided by m, mg. We can cancel the m's, and we get pxg minus pxg, which is clearly going to be 0. Perfect. So what have we done? We have shown that this quantity is a constant of motion because its Poisson brackets with the Hamiltonian is equal to 0. Okay, perfect. Okay, so after we have done this, we need to remember what the Liouville's theorem is about. Remember that we are going to use this concept to find a solution to the Hamilton-Jacobi equation associated to this particle, right? So the Liouville's theorem says, first, that we need to have some constant of motions that we name with the upper p's, right? The p1 and p2, okay? Okay, and it tells us that these functions, well, they need to be functions of the qi, the pi, and maybe the time, right? It is not necessary, but it can happen. The thing here is that this needs to be a constant of motion, okay? Perfect. This is the first part of the theorem. So we have accomplished this part, right? Because we already have two constants of motion. The first one is the one that we found, yeah? And the other one will be the Hamiltonian, which is equal to the total energy of the system, right? Because we know that looking that there are no external forces, the total mechanical energy is conserved, right? And this total energy matches with the Hamiltonian. So that means that we are going to establish that P1 is equal to H and P2 is equal to Px, Py divided by M plus Mgx, where this is the upper P and these are little p's, right? That is important. Okay. Perfect. So let me write this P1 as Px squared plus Py squared divided by 2m plus Mgy, because we are going to work with these expressions. Look what we are going to do. We are going to construct some mathematical structure that will allow us to use the Liouville's theorem, okay? So, first of all, let's say from this equation that, well, we will have that 2m p1 minus 2m squared gy is equal to px squared plus py squared, right? Just by solving this equation for this element that we have here. Okay, perfect. And then from this equation, we are going to get that p2 times m minus m squared gx is equal to px py. Okay, and from here we can get that 2m p2 minus 2m squared gx is equal to 2px py. I multiplied by 2 because, well, you're about to see that, well, we are going to sum these equations and we are going to get the perfect square trinomial, right? So what happens if we sum this equation? Let's say that this is going to be 2m times p1 plus p2, and then minus 2m squared g times x plus y, right? And then this is equal to px squared plus py squared plus 2px py. But like I mentioned, this is px plus py squared, right? Okay, so with this we can solve for px plus py to get px plus py is equal to plus or minus the square root of 2m upper p1 plus upper p2 minus 2m squared g x plus y. Okay, and what happens if we subtract the equations? Well, we are going to get the next. This would be 2m times p1 minus p2 minus 2m squared g, and then y minus x. That is going to be px squared plus py squared minus 2px py. Okay, so again, we are going to factor this, px minus py squared, right? It's not very hard to notice that. And then px minus py is going to be plus minus the square root of 2m p1 minus p2 minus 2m squared g y minus x. Okay, so here is where it comes the second part of the Liouville's theorem. It tells us that if we are able to find a function little p in terms of the q's, let's say pj, in terms of the q's, right, and the upper p's, and maybe the time, well, this is the second part of the theorem. And then with this, it is enough to get to a conclusion that tells us that, well, we can find a function s that is a solution to the Hamilton-Jacobi equation that can be written in the form ds equals p dq minus h dt. Okay, so that means that looking that we already found that two constants of motion and these p's, right, that are going to be this and this, looking that we already found this, we can say that there is a function s that satisfies this expression over here. And if we are able to construct these p's that we have here, then we are able to find this s. Okay, so that is what we are going to do now. Okay, so in the xy coordinates, we could say that this element can be written as px dx plus py dy minus h dt. But this quantity that I have here can be written as 1/2 px dx plus 1/2 px dy plus 1/2 py dx plus 1/2 py dy plus 1/2, let me make some space, plus 1/2 px dx minus 1/2 px dy minus 1/2 py dx plus 1/2 py dy. And why do I write this expression in this way? Because, well, we can see that, for example, from here, we can say that this element can be seen as 1/2 px of dx plus y, right? You're about to understand why when I give you the solution. So, for example, this can be seen as 1/2 py dx plus y, right? Remember that this differential is a linear operator, so this can be applied first to the x and then to the y. So we get these two elements that we have here. And from here, we can get that this is equal to 1/2 px dx minus y. And here, this is equal to minus 1/2 py dx minus y, right? Okay. And now with this, we can take a common factor d of x plus y here and here to get that this is equal to 1/2 px plus py, and then dx plus y, and then we will have plus 1/2 px minus py dx minus y. And then I forgot to subtract minus h dt here, and then minus h dt. Okay. Okay, so in this structure, we already have, well, this definition for the differential of the solution to the Hamilton-Jacobi equation. I mean that, let's say, for example, that we take the change of variable u equals x plus y, and maybe b equals x minus y. What happens with this? You can very easily see that, for example, let's take u dot equals x dot plus y dot and multiply by m on both sides to get m u dot equals m x dot plus m y dot. And we can define this quantity to be pu, right? The conjugate momenta of the u, which corresponds to maybe a linear momentum, right? In the u variable. I mean, it's not like the linear momentum, but it's the analog, right? But the thing here is that, well, this quantity can be seen as px, py, right? Like this. So the thing here is that that is what we have here, which is px plus py, which is pu, right? And x plus y, which is u. So that same thing happens here, where we can get pb equals px minus py. So that means that we can rewrite our conclusion as 1/2 pu du, right, plus 1/2 pb db minus h dt. Okay, so with this, we can establish that this is equal to the differential of s. And well, with this, we have shown that there exists the solution to the Hamilton-Jacobi that can be expressed as, well, this total differential, right? Where this function s satisfies that the partial of s with respect to u is equal to 1/2 pu, and the partial of s with respect to b is equal to 1/2 pb, while the partial of s with respect to time is equal to minus h. Remember that this function s is a generating function of canonical transformations. And well, it's not a topic that we are going to study today, but the thing here is that it is necessary to satisfy these equations that I have here to be a generating function of canonical transformations that is also to be a solution of the Hamilton-Jacobi equation. So with this, we can say that we have a structure, the total differential of that solution S. Okay, so what we are going to do now is to see another way of finding a function S, right, which is going to be also a solution of a Hamilton-Jacobi equation associated to this mechanical system. But now we are going to use a different constant of motion. In this example, we use P1 as Px, Py divided by m plus mgx, okay, and the Hamiltonian. So these two constants of motion are going to be the linear momentum in x, right? We know that the linear momentum in x is conserved, it's a constant of motion, right? In the motion of the particle in the gravitational field. And the other constant of motion is going to be py plus mgt, okay? Again, it's not too hard to show that this quantity is a constant of motion. So again, if we suppose that this function s exists, it can be written as px dx plus py dy minus the Hamiltonian times dt. Okay, so we are going to name these constants of motion as upper p1 and upper p2. Okay, here is it's not casual that we name this with the upper variables. I mean, remember that the upper variables represent the canonical transformation that is generated from the function s. I mean, you have the coordinate q and p, right? You have a generating function s that it generates the canonical transformations upper q and upper p. But we are choosing a special s that makes these two functions to be constants, okay? That is the important characteristic of the function s, that these quantities are constants. Well, these are some concepts that we have been remarking in recent lessons, right? Okay, so we are going to rewrite this equation, well, this expression, as p1 dx plus py dy, but py will be p2 minus mgt dy minus the Hamiltonian, right? But that is px squared, which is p1 divided by 2m, and then plus py squared, but that is p2 minus mgt squared, and then plus mgy dt. Okay, perfect. So we are going to be interested in expressing this as the differential of something here, right? To be able to say that that quantity is going to be, well, that function s that we need to find the solution of the Hamilton-Jacobi equation. Okay, so if we know that this function s is a function of the little q's, the upper p's, and the time, right? If we calculate the total differential of s, this will be the partial of s with respect to qi dqi, and then plus the partial of s with respect to pi dpi, and then plus the partial of s with respect to time dt. Remember that we mentioned that the Liouville's theorem says that we can express s only as the sum of this element with this element. So this element is going to be equal to 0, right? It tells us, the Liouville's theorem tells us this, right? Where these are only the little p and the little q. Okay, so that means that if we compare this equation with this element that we have here, that is equal to ds, we can see easily that the partial of s with respect to x needs to be equal to p1. The partial of s with respect to y is equal to p2 minus mgt, this element. Okay, and the partial of s with respect to time is equal to, well, all this thing minus, and let me copy this quantity to make it faster. Okay, there it is, right? So we need to solve these three differential equations that are not too hard. What are we going to do? Well, we are going to start by this equation. We can see here that this element, it does not have any t, right? and this element is also independent of the time. So we are going to have that S can be seen as minus p1 squared divided by 2m plus mgy times t, right? Taking the integral with respect to time of that, and then minus the integral of p2 minus mgt squared divided by 2m with respect to time, and then plus some functions of x and y, right? Because remember that s is a function of three variables. Actually, yeah, the upper piece, the little q's, where those little q's are x and y, right? And the time. So let me write it. S is a function of x comma y comma p1 comma p2 and the time. Okay, so that's why I added these two as, let's say, integration constants, because the integral is with respect to time, right? Okay, so we are going to get that S is equal to minus p1 squared divided by 2m plus mg y t, and then if we take this integral, we are going to get 1 divided by 2m, and then p2 minus mgt to the third power divided by 3. But here we need to divide by minus mg. Okay, and then what happens with these functions? Well, we see that this is a function of x, this is a function of y, but we mentioned that the partial of s with respect to x is equal to p1. So when we take the derivative of this function with respect to x, we need to get p1. So that means that f of x needs to be p1x, right? And that same thing happens here. I mean that the function of y will be this quantity times y, right? So this function corresponds to p2 minus mgt y. Okay, so let me write this here. We are going to get plus p1x plus p2 minus mgt y. Okay, and just to rewrite this in a more elegant way, let's say that s is equal to minus p1 squared divided by 2m plus mgy t plus this minus with this minus are going to be cancelled, and then 1 divided by 6m squared g times p2 minus mgt to the third power plus p1x plus p2 minus mgt y. Okay, perfect. So for this example, yep, this will be the solution to the Hamilton-Jacobi equation. Well, remember that, again, there can be many Hamilton-Jacobi equations associated to one mechanical system. So that means that there are a lot of solutions that corresponds to Hamilton-Jacobi equations. In this case, this is just one example of one solution, I mean. Okay, perfect. So I think this will be the final result of the lesson. Like, recall that this was an example of how to use the Liouville's theorem to find that function s. We establish this quantity, and then we try to make some tricks to find the differential of something that can be defined as this thing over here. And that quantity that we construct, well, it corresponds to the function s. That is, I mean, the powerful thing of the Liouville's theorem. Okay? Perfect. So I hope you enjoyed the lesson, and I think that I'm going to finish it right now.